this video, we're going to take a look at the effect of having a salt that's made up of an ion from a strong acid and one from a weak base. And we're going to see what the effect is in water. We'll see what the pH is. So in the previous video, we saw the pH of a salt from a strong acid, strong base, ended up being a pH of 7 because neither underwent hydrolysis. So let's go ahead and try an example where we have the salt of a strong acid and a weak base. So first of all, our salt is ammonium chloride, okay? And we have a 0.10 molar solution of ammonium chloride. What's the pH of the solution? So ammonium chloride is an ionic compound. It's a salt, and I'm going to show you what it looks like dissolved in water. That's our first step, is let's make this dissolved in water. So ammonium chloride, solid, put it in water, gives you, separate the ions, NH4 plus, AQ plus, Cl minus, AQ. And we're just going to write the concentrations at the bottom here, 0.10 molar. Now, our goal is to see if any of these parts of the salt will undergo hydrolysis and therefore affect pH. Let's try Cl minus first because we already did this example in the previous video. So we'll do a hydrolysis reaction. Actually, that's step 2. This is step 1, dissociate. Step 2, hydrolysis with one of the salts. So let's go ahead and do our Cl minus. Since that is negative, it's going to react with water and interact with the H plus. So it's going to be HCl, and then what's left over is the OH minus. But you'll notice that this over here is a strong acid. So what that means is that this part here is the salt of a strong acid. Therefore, this direction will not happen. It will prefer to stay as Cl minus. So this has no effect on pH. Okay. So we don't really have to worry too much about Cl minus because it's not going to affect pH. But now we do have to go test out the NH4 plus. We're going to do a hydrolysis reaction for NH4 plus. NH4 plus, AQ plus H2O liquid. So there's a couple things you can do here. The easiest thing to do is take a look at your NH4 plus, see if it's in that table of weak acids or weak bases. NH4 plus is the ammonium ion. And I noticed it has a Ka of 5.6 times 10 to the negative 10. So that's not a very large Ka. That means NH4 plus is a weak acid. Okay. So I know that by looking at that table. And because it has an extra H due to that plus, it's going to be giving away an H to the water. And it's going to become NH3 AQ plus H3O plus AQ. Now what I want you to notice is that this is a weak base, NH4 plus, or NH3 is a weak base. How would you know that? If you go look over here, NH3 is in our weak base table. So what that means is that this is a salt of a weak base. And the salt of a weak base is going to act as a weak acid because it makes H3O plus. So acts as a weak acid. So this actually does happen. So we found that this does have an effect on pH, but this does not. So this is going to determine the pH of our solution. Now all we have to do is make an ice table for this equation we wrote here for the NH4 plus because it's affecting our pH, and find the pH with that ice table. So ICE. We need to find the concentration of NH4 plus. We can do that using our molar ratios from our dissociation equation. This is a 1-to-1 ratio. So that means that the concentration should be 0.10 molar here. And also for the Cl minus, so we don't care about it because that's not affecting our pH. So that's our initial concentration of the NH4 plus, 0.10 molar. We don't care about water because it's liquid. And assuming there was nothing in the beginning other than NH4 plus, this is 0 and this is 0. This would be plus X. This is plus X. This is minus X. Make sure it's balanced. And this is 0.10 minus X. This becomes X, and this becomes X. So we are just going to try to find the X value over here to find the H3O plus in order to determine the pH. So we have NH4 plus. We're writing a Ka expression because it's a weak acid. So Ka is going to be equal to the H3O plus times the NH3 over the NH4 plus. If you replace all that by x's, you get x times x over 0.10 minus x, and you get x squared over 0.10 minus x. Now, from your chart, you can get the Ka of NH4 plus. Make sure you choose NH4 plus because that's the salt that you have. So, in other words, don't go to get the Kb of NH3. Use NH4 plus, and that is 5.6 times 10 to the power of negative 10. So we know that 5, so let's call this step 5. 5.6 times 10 to the power of negative 10 is equal to x squared over 0.10 minus x. And now we're just going to solve for x. Let's check the 100 rule first. So the 100 rule, we have our initial concentration, 0.10, over the Ka, which is this over here, and that's going to be greater than 100. Therefore, we can simplify. So I'm just going to finish this up over here. So we're going to continue with the simplification. So we have 5.6 times 10 to the power of negative 10 is equal to x squared over 0.10. So that means that x squared is equal to 0.10 times 5.6 times 10 to the power of negative 10. And if you want to find x, you just do the square root of that. So x is equal to the square root of 0.10 times 5.6 times 10 to the power of negative 10. And that will be the concentration of the H3O plus in our ice table from the NH4 plus. So 0.1 times 5.6 times 10 to the power of negative 10, square root that, and we get 7.4833, so on and so forth. I'm leaving it all in my calculator, times 10 to the power of negative 6 molar, moles per liter, because it's the concentration of H3O plus. So we found the X value over here, and now all we need to do is use this X value, because it's our H3O plus, to find the pH. Remember that the pH is equal to negative log of H3O plus, which is the negative log of this number here, 7.4833 times 10 to the power of negative 6. And we get about 5.1259 for our pH. So pH is approximately to how many sig figs? To 2 sig figs, 5.1. So what we've seen here is that if you have a salt that's the salt of a weak base, so the strong acid part, pH is equal to 7, so no effect on pH, in other words. But if you have that weak base, so strong acid, discount it, weak base, salt of a weak base, it's going to act as a weak acid. So the NH4 plus is a salt of NH3, which is a weak base. Therefore, the NH4 plus acts as a weak acid. And so therefore, the salt that contains a strong acid and weak base derivative would have a pH that is less than 7. Not exactly 7, but less than 7, because the salt of the weak base acts as a weak acid in this solution. So that's a generalization that we can make for strong acid, weak base salts. For example, if we look over here, actually we'll go over that later on. We'll finish that in the next video. So our generalization right now is that when you have a salt that's made up of a strong acid derivative, so Cl minus was the salt of a strong acid, that will not affect your pH. But if it's attached to something that was made from the salt of a weak base, so NH4 plus is from the salt of a weak base, which is NH3, the pH overall will be less than 7 because the salt of a weak base, in this case NH4 plus, the salt of the weak base, acts as a weak acid. So strong acid, weak base combination is going to give you pH less than 7. And that's what we got here. That makes sense. A pH of 5.1, which is less than 7. So you must write the dissociation equation first, test out each ion using hydrolysis. We saw that the Cl minus is the salt of a strong acid, so no effect on pH. And then we saw the NH4 plus from our table is actually a weak acid. But just to confirm, when we do the hydrolysis, we get that NH4 plus gave its HOA to the water. So it became NH3 and H3O plus. And NH3 we saw in our table is a weak base. So that makes NH4 plus the salt of weak base, making it a weak acid. So this is what we're going to use our equilibrium to make an ice table to solve for the X value that is the H3O plus in the end. Now we had to find the initial concentration of NH4 plus, and we found that from the dissociation equation. If there was 0.1 molar of NH4Cl, then because they're in a 1-to-1 ratio here, there's 0.1 molar of the NH4 plus. And we don't care about Cl minus because it's not affecting pH. So we use those values using our Ka of NH4 plus to find the X, which ends up being our H3O plus. And then we can do our negative log of the H3O plus to get the final pH over here rounded to 2 sig figs. And this makes sense because the pH is less than 7 since we had a salt of a weak base which acts as a weak acid. In the next video, we're going to take a look at a salt where you might have the salt of a weak acid and the salt of a strong base. Whereas here we had the salt of a strong acid and the salt of a weak base. We're going to flip it around and see what effect that has on pH.